Let's go ahead and do some more examples of finding definite integrals, evaluating them. So if it's helpful for you, I definitely recommend just writing in the top of your paper the fundamental theorem of calculus, just in its general form. I often do this with new formulas or anything that I think I'm going to be using kind of often. Oops. It just helps it kind of stick in your mind as a first plan of attack. It helps when you get to a test, you don't have to think about what to do. You kind of can write at least this down and see where you can go from there. But anyways, okay, that's more of a test-taking strategy and just a general learning strategy. But let's go ahead and do this problem at hand. So how are we going to do this? Well, first of all, we need to find the antiderivative, or an antiderivative of x squared plus 2. So x squared, we know how to do that. That's just x cubed over 3. And an antiderivative of 2 is just 2x. And in the last video, we discussed why we don't need to add plus c, because the plus c's are just going to cancel. So we add this vertical bar to remind us we need to plug in some numbers. We're not done yet. So we're going to plug in 3. So this is going to be 3 cubed over 3 plus 2 times 3. So that's what happens when we plug in 3 minus what happens when we plug in 0. So this is 0 cubed over 3 plus 2 times 0. Okay, well, 0 over 3 is 0, 2 times 0 is 0, so that just goes away. 3 cubed, well, this is really 3 squared because we can, let me do that in a different color. We can cancel one of these powers in the bottom because the number here, the base is 3. That's why we can do that. Or you could just evaluate it. That'd be 27 over 3, which is going to be 9. Same thing as 3 squared. Okay, so anyways, that's arithmetic. Back to calculus. 9 plus 6 is equal to 15. So the area under the graph of x squared plus 2 on the interval for when x goes from 0 to 3, the area under that graph is 15. That's pretty cool. And it shouldn't surprise you that we can do this process. So I didn't actually talk about this while it was happening, but we can take the antiderivative of x squared and the antiderivative of 2 separately, because when we take derivatives, we can take derivatives of sums separately. So in other words, let me show you what I mean. If we were going to do this in reverse, if we were going to take the derivative, if we were going to take the derivative of x cubed over 3 plus 2x, if we were going to do that, well, we would just take the derivative of x cubed first. So we would say, okay, this is 3x squared over 3, or in other words, just x squared. And the derivative of 2x, we just take that. That'd be 2. So we do it piece by piece. So it shouldn't surprise you that when we're undoing the process, when we're taking an antiderivative, we can also do it piece by piece. Okay, let's look at some more examples here. Let's say we want to look at the antiderivative of from 0 to pi over 2 of cos x plus, let's do just x. Okay, well, what's the antiderivative of cos? Well, the derivative of sine is cos, so the antiderivative of cos is sine. And pause the video if you need to take a moment to think about how that works. Sometimes the words can be confusing to think about as they're said. The antiderivative of x is just x squared over 2. And then we're going to evaluate this from 0 to pi over 2. And once we find the antiderivative, the rest is really just arithmetic. So I'm just going to switch colors here because I feel like it. So this is going to be the sine of pi over 2 plus pi over 2 squared over 2 minus the sine of 0 plus 0 squared over 2. Okay, well, lucky for us, this is easy enough to evaluate. Sine of 0 is 0, 0 over 2 is 0, and then what do we have left? Well, the sine of pi over 2, that's 1, and then pi over 2 squared, that's pi squared over 4, divided by 2 is pi squared over 8. Pi squared over 8. So that's our answer. That's fine the way it is. You could also combine this so we get 8 plus pi squared over 8. We really didn't need to do that, but anyways, that can be done. Okay, so hopefully we're getting some good practice here. Maybe let's just do one more. Why not? How about the antiderivative from 0 to 1 of e to the x plus 3 let's do 3x. Why not? Okay. So the antiderivative of e to the x, well, is just e to the x. That's because the derivative of e to the x is e to the x, so the antiderivative of e to the x is e to the x. I hope that makes sense. The antiderivative of 3x, well, we could take the antiderivative of x, so this is really 3 times the antiderivative of x. We can think about it like that, but we don't need to write out that many steps. The antiderivative of x is x squared over 2. So this is 3x squared over 2. And this is going to be evaluated from 0 to 1. So I hope what I had said to you makes sense about this antiderivative. If you don't believe me, take the derivative of 3x squared over 2. And hopefully it will start to make a little bit more sense. So this is e to the first power plus 3 times 1 squared over 2 minus e to the 0 plus 3 times 0 squared over 2. Okay, now it's really tempting, especially since we just did in the past few videos, to say, oh, that's 0. But that's wrong, because e to the 0 is really 1. E to the 0 evaluates to 1. So don't forget about that. You get a couple points off on a test maybe. It looks nice. I wish we could do that, but we can't. So anyways, this is e. 1 squared is 1, so this is just 3 halves. E plus 3 halves minus 1. This part, of course, is 0. And that is equal to e plus 1 half. Okay, so that's the area under the graph of e to the x plus 3x when x goes from 0 to 1. So really, definite integrals are really easy now. Finding exact area under curves is going to be really, really easy. No more hassling with Riemann sums. And the hardest part of all of this is going to be finding the antiderivative. And for a while, that process really isn't going to be too difficult. It's not until you move into second semester calculus, or what's often referred to as calculus 2, that you get into some more sophisticated techniques for finding antiderivatives. For now, things are going to be relatively simple, so no more worries. You can finish out the course strong. See you in the next video.